Hello students, in this lecture we will solve few numericals on Hall effect. Let us see the first numerical. A copper specimen of length 1 meter, width 1 centimeter, thickness 1 millimeter. It is conducting a current of 1 ampere along the length. It is applied with the magnetic field of 1 Tesla along its thickness. So see how the magnetic field is applied along the thickness. How the Hall voltage will appear? Hall voltage will appear across the width then. It experiences Hall effect and Hall voltage of 0.074 microvolts appears along its width. Calculate Hall coefficient and mobility of electrons in copper. Conductivity of copper is given 5.8 into 10 raised to 7 mho per meter. Let us summarize given data. Dimensions of the specimen are given: length, width, depth. Length is 1 meter, width is 1 centimeter, depth is 1 millimeter. We have converted width and depth into meters because we will use all quantities in SI units. Magnetic field of 1 Tesla is applied along the thickness. Current of 1 ampere is flowing along the length. So that Hall voltage appears across the width. It is 0.074 into 10 raised to minus 6 volts. Conductivity is given. We need to calculate Hall coefficient and mobility of electrons in copper. Let us solve the numerical. So, we need to understand this formula for Hall voltage. Hall voltage VH is equal to RH into BID upon A. What is RH? RH is Hall coefficient. BID upon A. What is A? A is a cross section area of the conductor, which is W into D. See that in this formula, this D in the numerator, this is the side, this should be the side across which Hall voltage develops. So this will depend upon the direction of magnetic field. When the magnetic field is applied along the width, then Hall voltage will appear across the thickness or depth. Thickness is also called as depth. So in that case, this is the side D. In the numerator, the side should be across which Hall voltage develops. So in this case, we will use this formula VH is equal to RH BID upon A because Hall voltage appears across the thickness. But instead, if the magnetic field is applied along the thickness, as it is happening in this numerical, if the magnetic field is applied along the thickness, then Hall voltage will appear across the width, and this should be the side across which Hall voltage develops. So this D should be replaced by W in this case because Hall voltage appears across the width. So in this numerical, because the magnetic field is applied along the thickness, Hall voltage will appear across the width. So we will use this formula. VH is equal to RH into BIW upon A. Remember that this side D or W is the side across which Hall voltage develops. It can be D or it can be W. It is the side across which Hall voltage develops. So in this numerical, because it develops across the width, Hall voltage develops across the width. So what formula we will use? We will use VH is equal to RH into BIW upon A. So this A is the cross section area of the conductor. A is equal to W into D. So RH into BIW upon W into D. So this W will get cancelled and VH is equal to RH into BI upon D. Because we want to calculate Hall coefficient, we will rearrange this for Hall coefficient. Hall coefficient RH is equal to VH into D divided by B into I. Now all values are known to us: Hall voltage, thickness, magnetic field and current. All quantities on the right hand side are known to us. So we will put the values here. Hall voltage is 0.074 microvolts. So that is why 10 raised to minus 6 is there. Thickness is 1 millimeter. So that is why 10 raised to minus 3 meters. Current is 1 ampere. Magnetic field is 1 Tesla. So Hall coefficient will come out to be 0.074 into 10 raised to minus 9 meter cube per coulomb. Now we need to calculate mobility. We know the formula for mobility is sigma into RH. Conductivity of the copper is given and Hall coefficient we have calculated. We only have to put the values and we will arrive at the mobility of electrons in copper to be equal to 0.004292 meter square per volt second. So here we have calculated Hall coefficient and mobility. Let us see the next numerical. A slab of silicon 2 cm in length, 1.5 cm wide, 2 mm thick is applied with the magnetic field of 0.4 Tesla along the thickness. Magnetic field is applied along the thickness. Hall voltage will appear across the width. The current of 75 ampere flow along it the length. The voltage measured across the width. Of course, the Hall voltage measured across the width is 0.81 millivolts. Calculate the concentration of mobile electrons in silicon. We have to calculate N here. We have to calculate N. Let us summarize the given data. Dimensions are given. Length is 2 cm, width is 1.5 cm, depth is 2 mm. The lengths are converted to meters. B is 0.4 Tesla. Magnetic field is applied along the thickness. Current is 75 amperes. Hall voltage is 0.81 millivolts. We need to convert SI units. 0.81 into 10 raised to minus 3 volts. It is appeared across the width. We have to calculate charge carrier concentration in silicon. Solution. Let us solve the numerical. So as earlier numerical, what we said, this W in the numerator, it should be the side across which Hall voltage develops. It can be D or it can be W. Here Hall voltage appears across the width. So this will be W in the numerator. So VH is equal to RH into BIW upon A. A is the cross section area. So now we need to calculate charge carrier concentration N. So instead of RH now we will write it as 1 upon NE. RH is equal to 1 upon NE because we want to calculate charge carrier concentration. So this BIW upon A. A is W into D. So that this W will get cancelled. And finally VH will be equal to 1 upon NE into BI upon D. Now as we want to calculate charge carrier concentration N, we will rearrange this equation for N. N is equal to 1 upon VH into E BI upon D. Now see that all quantities on the right hand side are known to us. Hall voltage, charge of electron, magnetic field, current and the thickness of the specimen. D is the thickness of the specimen. So we will put the values here. All given values are put here and we will arrive at this answer 11.57 into 10 raised to 25 per meter cube. So concentration of mobile electrons in silicon is 11.57 into 10 raised to 25 per meter cube. Let us see the next numerical. Calculate the mobility of charge carriers in a doped silicon whose conductivity is 100 per ohm meter and Hall coefficient 3.6 into 10 raised to minus 4 meter cube per coulomb. So conductivity is given 100 per ohm meter. Hall coefficient is 3.6 into 10 raised to minus 4 meter cube per coulomb, and we need to calculate mobility of charge carriers. Simple it is. We know the formula mu is equal to sigma into RH. So simply we need to do the multiplication of these two so that we are getting the mobility. So we have to put values and we will arrive at the answer. Mobility of charge carriers is 0.036 meter square per volt second. Let us see the next numerical. The resistivity of doped silicon is 9 into 10 raised to minus 3 ohm meter. Hall coefficient is 3.6 into 10 raised to minus 4 meter cube per coulomb. Assuming a single carrier concentration, means one silicon atom will give one carrier. Find carrier concentration, mobility and density of charge. So we need to calculate carrier concentration, we need to calculate mobility, and we also need to calculate density of charge, that is charge per unit volume. What is given to us is charge of electron 1.6 into 10 raised to minus 19 coulomb. Summarize the given data. Rho resistivity is given 9 into 10 raised to minus 3 ohm meter. Hall coefficient is given. We need to calculate charge carrier concentration. We need to calculate mobility of charge carriers, and we need to calculate charge density, that is charge per unit volume. So what is charge density? It is N into E, because N is a carrier concentration, number of charge carriers per unit volume, and we need to multiply it by charge of each particle, that is electron. So the charge density will be nothing but Ne. So that is why it is equal to reciprocal of Hall coefficient. So if we need to calculate charge density, what we will calculate? We will calculate simply reciprocal of Hall coefficient. Let us solve the numerical. Firstly, let us calculate mobility. We know that mobility is sigma into RH. So conductivity sigma is 1 upon rho. So it will be equal to RH upon rho. Simply we have to put the values, all are given. Hall coefficient is given, resistivity is given. So we will get mobility is to be equal to 0.04 meter square per volt second. Charge density, as I said, it is equal to Ne, and hence it is equal to 1 upon RH. We simply need to calculate reciprocal of Hall coefficient. So it comes out to be 0.277 into 10 raised to 4 coulomb per meter cube. It is charge density. So it is coulomb per meter cube. We need to calculate charge carrier concentration. So N is equal to 1 upon RH into E, because RH is equal to 1 upon Ne, right? So putting the values only, we will get simply the calculations will give us the answer 0.1736 into 10 raised to 23 per meter cube. Let us see the next numerical. A silver wire is in the form of a ribbon 0.5 cm wide, 0.1 mm thick. A current of 2 amperes is flowing through the ribbon perpendicular to 0.8 Tesla of magnetic field. Calculate Hall voltage produced across the width. See that Hall voltage is appearing across the width. Density of silver is given, atomic weight of silver is given. So let us summarize given data. Width and depth are converted to meters because we use SI units here. 0.5 into 10 raised to minus 2 meters. 0.1 into 10 raised to minus 3 meters. Magnetic field is 0.8 Tesla. Current is 2 amperes. Density of silver is 10.5 gram per cc. Atomic weight of silver is 108. We need to calculate Hall voltage which is appearing across the width. Let us solve the numerical. The formula for VH, RH into BIW upon A. See that this W is the side across which Hall voltage develops, right? So this is BIW upon A. A is the cross section area which is W into D. W will get cancelled. Finally, VH is 1 upon NE BI upon D. See that on the right hand side now finally B is known, I is known, charge of electron is known, thickness of the specimen is also known. We need to calculate carrier concentration N, for which we have to use Avogadro number. 1 mole of silver. What is 1 mole of silver? It is 108 gram of silver will contain Avogadro number of atoms. So 10.5 gram of silver will contain how many number of atoms? 10.5 gram is density of silver. The calculations will give us, for silver, number of atoms per cc is 5.852 into 10 raised to 22 atoms per cc. But we need to use SI units, so we need to convert atoms per cc to atoms per meter cube. That is why we need to multiply it by 10 raised to 6. So number of silver atoms per meter cube will be 5.852 into 10 raised to 28 atoms per meter cube. Now everything on this right hand side is known and we have calculated. E is known, B, I and D are given to us. So we have to put the values in the formula and we will calculate Hall voltage. Putting all the values, we arrive at the answer. Hall voltage across the width comes out to be 1.71 microvolts. Thank you, students. I hope this lecture will help you to solve numerical on Hall effect.